pour la soutenance de Taha, puisque nous avons un membre qui n'est pas francophone, qui est le président de jury, professeur Svanweg. Donc on va plutôt le présenter. La présentation sera faite en anglais, également les questions-réponses. Je donne sans attendre la parole à mon collègue, professeur Svanweg, de l'Université technique à Prague. San, please, if you want, just introduce and start the session.
So good morning. I'm Professor Stanislav Zvanovec. I'm Deputy Head of the Department of Electromagnetic Field, Czech Technical University in Prague, and I am the chair or president of this jury, which is about the PhD defense of T.ESSALIH and PhD thesis entitled High Spectral Efficiency Signaling Schemes for Underwater Wireless Optical Communication Systems. The jury consists of myself, then Professor Lauren Ross from Grenoble Alpes University. Good morning, Lauren. Then Dr. Eric Simon from Lille University. Both were revivers of the PhD thesis. And next member of the jury is Dr. Muriel Roche from École Centrale Marseille. I forgot to mention that supervisor of the thesis is Dr. Ali Khaligi, and co-supervisor is Professor Hassan Akouari, both from École Centrale Marseille. We have another three invited members, Dr. Jan Opperbeke from IFREMER. I don't know if he joined us or not, maybe during the presentation. Then Mr. Christian Marfia from IFREMER as well, and Mr. Yves Jadard from Subsea Tech. So welcome to this defense. And now I would like to ask a student, T.ESSALIH, to present us in maximum 45 minutes the results of his research and his PhD study. So please, Taha, now is your part.
Okay, thank you so much, Professor Stan. Hello, everyone. So today I'll be presenting my PhD work entitled High Spectral Efficiency Signaling Schemes for Underwater Wireless Optical Communication Systems. This work has been co-funded by region BACA and École Centrale Marseille, and it has been done in Institut Fresnel. So the defense work will be presented as follows. First, with an introduction. Second, we will talk a little bit about underwater wireless optical communications. Then we will give some details about a photodetector called silicon photomultiplier, which is the key of this work. It's using it to detect Earth symbols. And then we will speak about spectral enhanced modulation schemes known as optical orthogonal frequency division multiplexing. Then we will introduce some other spectral enhanced optical schemes and compare them together to as a function of performances. We will talk about the experiment setup that has been done to validate the numerical results obtained, and then we will conclude the work and give some perspectives. So underwater life and its resources have always raised the interest of humankind. Our knowledge about the subject remains very limited, since the human body cannot support an extreme pressure and lack of oxygen. So underwater equipment has been made in order to explore this unknown part of the world and also explore its resources. And as you can see in the figure, we have underwater equipment that require a data rate transmission, a wireless data rate transmission, so we can send information to the surface area where this information will be treated later on. So this equipment require a wireless communication system As known, acoustic waves offer a wide range in underwater communication, but it presents a low data rate when the latency in transmission. Radio frequency waves also are very attenuated in the water. So that leaves us with the optical wave, which could be a better alternative for application requiring high data rate, such as transmitting video sequences. And as you can see here from the figure, we have the absorption or the attenuation of the underwater channel versus the wavelength. And we can see that in the visible range, we have the lowest attenuation, which make optical waves a better candidate for this type of application. The problematic is that optical waves offers a limited range or moderate term range, and to do so, we are using a sensitive photodetector, which is called silicon photomultiplier. Using this component limited the bandwidth of the system, and that's why we are introducing a high spectral efficiency modulation scheme, so we can enhance the data rate, especially for the example of sending video sequences. And in this work, we are using a real component characteristics, so we can know exactly the performance, how it would be in practice. And as a criterion, we are fixing the transmit power of the system, as it is crucial parameters for the underwater missions. Now let's talk about underwater wireless optical communications. So here we find a block diagram of a typical underwater wireless optical communication system. Here we have our data source, and then it will be modulated and coded later. And we fit the electric signal from the modulation to the optical source we are using. And then we would send it through the underwater channel, and then we will detect the optical signal via a photodetector, which will convert the optical signal to an electrical signal. And after processing and demodulation, we can extract this data that we sent in the first place. So when we are talking about underwater wireless optical communication systems, we are concerned about intensity modulation diode detection. So the signal should be modulated in amplitude, and it should be positive and real signal, since we are using non-current sources, and also because the optical signal should be positive and real. Then for the modulation schemes that we can use, we can either use single carrier schemes, for instance, on-off gain, which is modulating the power of the 0 for a low power and 1 for a high power. And multi-carrier modulations, and this is the scheme that we are focusing on this thesis, which is optical orthogonal frequency division multiplexing, or OFDM, which is a technique that takes the available bandwidth and dividing it and sending the data in parallel. So for emitters and receivers used in underwater wireless optical communication system, we can find the follow equipment. And in our work for our optical source, we would be using a light imaging diode or an LED. And as a photo detection, as mentioned before, we will be focusing on the silicon photomultipliers. Now let's talk about what it's called the aggregate channel. So when we are talking about optical communication system, underwater optical communication system, we can consider the channel as 3 parts: the optical source, the aquatic channel, and also the photodetector, which all can be approximated by the aggregated channel. So each part of the channel represents an impulse response, which is different from the impulse response, the aquatic channel, and the photodetector as well. So the impulse response of the aggregate channel can be modeled by the product of convolution of all the three parts of the channel. The impulse response of the aquatic channel is neglected because for short distances, the delay spread is negligible. And also the impulse response of the optical source and the photodetector is modeled by a first order low pass filter. So for the component that we use in this work, the LED and the ICPM, which is the silicon photomultiplier, we have a frequency cutoff of 10 megahertz for the LED and 4 megahertz for the ICPM. So when working in underwater wireless optical communication systems, we are concerned as well by channel attenuation, and this phenomena can be considered by scattering and absorption. Scattering is when the photons of the signal are scattered from their original patch, and absorption is when the photons are absorbed by water, by the presence of certain substance in the water. So we model this loss by a Beer-Lambert model, which is an approximate model that can model the channel loss that we have. And based on this equation, K here depends on the water type and the concentration of certain substance in the water. In our case, in this study, we consider working under a clear water environment. And that is the distance between the emitter and the transmitter. We have other possible impairments when working in underwater wireless optical communication system. We have turbulence, beam obstruction, solar noise, and link misalignment. And for this work, we are considering working under a clear water environment. We are considering that we are working in deep water, so we are not concerned by beam obstruction, neither solar noise. And we assume that we have a perfect alignment between the receiver and the now let's detail a little bit about the silicon photomultiplier, which is the photodetector that we are using in this work. So silicon photomultiplier is, as you can see in the figure, is a matrix of APDs that are biased above the breakdown voltage. So each APD with a circuit can form a microcell, and this microcell, when it detects a photon, it generates a massive current flow. So when receiving a photon, with the ICPM or the microcell of the ICPM generates one pulse, which corresponds to one photon that has been received. So in this context, why we are using ICPM? ICPM offers a high internal gain, which means high sensitivity. So it allows us to extend the link range of underwater wireless optical communication system. And it can work under low operational voltage, which is, as discussed before, the power efficiency of the underwater equipment is very important. So from photo counting, as said before, for ICPM, when it counts photons, each microcell that counting a photon generates one pulse. So the photon counting process can be modeled here by a Poisson distribution, and the average of photon count mu that is counted is defined by this equation below, when we have the PDA or photo detection efficiency is the probability that a photon received by the ICPM is detected or not. We have the energy of the photon. We have the power of the received signal. We have what it's called DCR, or dark current rate, which is the current generated in the dark. We have the probability of after pulsing. which is the probability that a photon detected by one microcell generates another pulse later on, even the photon is not detected. And we have the probability of crosstalk, which is the probability that a photon detected by one microcell generates another pulse in the microcell that is neighbor. And here we have TS, which is the time symbol. So when working with ICPM, we are concerned by a nonlinear behavior or a nonlinear distortion. We have a key parameters is called dead time, which is the time needed for a microcell to recharge and to come back to the initial stage, so it can be ready to detect a photon. So the non-respect of this dead time between two consecutive photons generates a nonlinear behavior. We define what is called the passive Kenshin configuration, where the average numbers of photons received can be considered by this equation, where we have mu, the average photon. Here we have the dead time, the numbers of microcells in the ICPM, and also the time symbol. So here in this slide, you find the characteristics of ICPM that we are using. For instance, we find dead time, the current rate, and so on. We consider the use of Hamamatsu ICPM under this reference. And here on the right, we can find the LED characteristics that we are using from Nisha. And here in the blue curve, we have the real characteristics, and the red curve, we have the linearized characteristics that we use in this work to calculate the power of our signal. So here we find a simulation that has been done to show the effect of the nonlinear distortion. We have plotted the average photon count and versus the power in dBm. So here, as we can see, the power is very low, so we can be considered as a dark region, and we can find also photon detected for this curve. The difference between the blue curve and the red curve is the time symbol, as you can see here. So when increasing the power, we increase the numbers of photons as well, which has a linear behavior. Until we reach a certain power, then we are in the nonlinear distortion zone, where the photon has no longer have the linear behavior, and it drops because here the power is too high and we don't respect that time anymore. So here we plotted the performances of a simple modulation scheme, which is OOK using this component. OOK is to calculate the power of the signal here, the transmit electrical power. We fixed the 0 at the minimum value of the LED as shown in the figure of the characteristics of the LED, and the power of 1 as we can have a total power of 125 milliwatts. So here we plot the bit error rate or BER performance versus the link range for several data rates. And as we can see, there's two parts of this figure. Let's take the right part, for example. This concerns the attenuation of the channel. So when reaching a high distance, for instance, for OOK with 1 megabit per second, when reaching higher distances, we can see that the BER becomes higher, and this is due to the channel attenuation. So for the left part of the graph, we are concerned here by the ICPM saturation, which is due to the high power that the receiver receives. So as we can see here, that the saturation effect is concerned by all the data rates. So even when we change the data rate, which is related to the time symbol used, we have the same saturation. And also we can notice that for 50 megabit per second and 20 megabit per second, the link become non-operational. This is due to the fact that the limited bandwidth of the ICP-AM and the LED. So when increasing the data rate, the link become non-operational. So in order to resolve this problem, the problem of data rate, enhancing data rate, we are introducing in this section the optical orthogonal frequency division multiplexing, which is a scheme that takes the available bandwidth and dividing it into narrow subcarriers. So we can send data in parallel through each subchannel. In this way, we can enhance capacity of the system. So as said, why OFDM? Because the ICP-AM, we use ICP-AM to extend link range, which has a limited dynamic range, and OFDM is to enhance data rate. So when using optical orthogonal frequency division multiplexing, we are concerned about what is called high peak to average power ratio. So considering this parameter, we would see in this section if it is interesting to use optical OFDM or not. So at first, we will give details about classical schemes used widely in visible light communications, which is called DC biased optical OFDM or DCO OFDM. These techniques consist on modulating the signal through QAM modulation or quadrature amplitude modulation. This gives us a complex signal which we use in a Hermitian symmetry, so we can have a real signal after the block of inverse fast transformer. So when we're using inverse fast transformer, later on we would have a real signal, and then we would add what is called the cyclic prefix, which is basically to avoid intersymbol interferences. Then we scale our signal to fit the LED characteristics. We add a bias to ensure positivity because the signal here may be negative. And we double side clip our signals before feeding it to the LED. Double side clipping here is based on the LED characteristics. So the signal is going through the aquatic channel and then received by the ICP-AM. And through photon counting, we can receive our signal and then perform a photon to amplitude conversion, which is simply multiplying the number of photons by the energy of the photon. We remove the cyclic prefix that we added here, and then we introduce a fast Fourier transformer when we can perform an easy one-tap equalization, and then we restore the quadrature amplitude modulation demapping, and we have our input bits that we send in the first place. So to adapt the OFDM signal to the DCO OFDM signal through the LED characteristics, we are referring to the same curve, and we are using the linearized characteristics. So the scaling of the signal, as said before, is just multiplying it by a factor of alpha. So the transmit of electrical power of the signal would be dependent mostly on the scaling factor used and the DC bias that has been set. And we are obtaining, we consider the DCO OFDM signal as a voltage, and we obtain the current by its bijection, and then this way we can calculate the transmit electrical power. So here we are using a classical approach to fix the DC bias of DCO OFDM. And this approach is used mostly in the literature, where we can refer to what it's called here clipping factor. And we multiply this clipping factor by the square of the mean of the scaled signal. We add in our context minimum value of the voltage of the LED, because we are taking real time characteristics of the LED. And this bias, it will be depend mostly on the clipping factor used, the alpha, which is the scanning factor used, and then the minimum voltage of the LED. So we did investigate another optimal scheme or technique to optimize the DC bias to have the best performances. And we have shown that it presents later of interest. This optimal techniques consider the minimizing the mean square error between the scaled signal and the clipped signal. And this technique has presented low interest since it takes a huge computational complexity to achieve almost the same performance as the classical approaches. So for our case study, we will use for DC biased optical OFDM technique a 4-qua modulation order. We are using 1024 subchannels, so we are sure that the channel is flat. The impulse response of the channel is flat for each subchannel. To fix the data rate, we are adjusting the time symbol, and the time symbol is calculated. The bandwidth is calculated based on the time symbol used and the numbers of subcarrier. For the DC bias, we used 7 dB, and for the limited dynamic range of the optoelectronic component, we are considered by the frequency cutoff of 10 MHz and 4 MHz for LED and ICPM, respectively. So here we plot results with a comparison with OOK and DCO OFDM for several data rates. We have here the plot of the distance, the BR versus the distance. The BR is the bit error rate. And we define here a parameter which called LBI or low BER interval, which is the distance between the saturation, as you can see, and the maximum link range, which is here. So we can, the LBI is defined target BER of 10 minus 3. So we can see that, let's take, for instance, the blue curve. Here we have the performances of the DCO, OFDM, and OOK modulation scheme, and we can see the huge difference in terms of the attainable maximum link range, which shows the advantage of DCO over OOK. Here in the saturation part, when the power is too high because the distance is low, we can find that the saturation of OOK is less than the saturation of DCO, but the difference is not that huge. This is due to the fact that OOK modulation has a lower PAPR, or peak to average power ratio, compared to DCO. So to summarize the results, we have shown the advantage of DCO in terms of flexibility, which is the LBI or low BR interval, and the maximum attainable link range. And also, we shown that for DCO, we can reach high data rate compared to OOK, which become non-operational when working under 15 megabit per second. Not the case for DCL, as you can see here for the green curve and this curve. So DCO is more robust against channel selectivity, and as said before, we have OOK that present less saturation. Now we will introduce another spectral enhanced OFDM techniques and compare them with DC biased OFDM technique. And to see the performance for each one and how to apply them in the underwater wireless optical communication systems. First, we will introduce what is called asymmetrically clipped optical OFDM technique, or as known as ACO, which is also a classical and wild technique in underwater wireless optical, VLC, in visible light communications. And this technique consists on modulating the data only in the odd subcarriers, which means 1, 3, 5, and so on. So this way, if we modulate our signal this way, we would lose the half of the bandwidth compared to DCO, for instance. But we can clip our signal at 0 without any information loss. So this technique is more power efficient than DCO because a DC bias is not required to ensure positivity. And now we will present another technique which is called layered asymmetrically clipped optical OFDM, or LACO, which is a derivative from ACO technique. And this technique aims at enhancing the bandwidth of the system compared to ACO, and keeping the advantage of power efficiency with respect to ACO, of course. So here we have our modulated data that is modulated through different layers. In this example, to illustrate better the scheme, we're taking only three layers. And for the first layer, we modulate as ACO the odd subcarriers. And for the other layers, we are using the even subcarriers that now has been used before to modulate the data. So for the second layer, we'd use 2 and 6, we would not be using 4, and so on. And for the third layer, we would using, for instance, 4 and 12 and 8 would not be used. So this way, each layer generates one signal, and it will be superimposed later on at the transmitter side. So here, a block diagram of layered ACO OFDM technique, where we can find here the signal generated from the first layer using also Hermitian symmetry, the inverse fast Fourier transformer, and we clip at 0 the signal. For the second layer, the same thing, and also for the nth layer, we have the same thing. All the signals from all the layers are superimposed, and then we add this cyclic prefix to ensure that we don't have an interference, intersymbol interference. We scale the signal as well. And here we add the bias because since we are taking into account real characteristics of the LED, we are concerned by the minimum value of the LED that we should add, even the signal does not require a bias to ensure positivity. It's the case for LACO and for ACO as well. We upper clip the signal because the signal has been already clipped at 0, and we transmit our signal the same way as DCO. We perform a photon to amplitude conversion. And since the layers would be interfere with each other at the transmission, we need a receiver, a special receiver that can detect the signal one by one. So this is the iterative receiver used to detect the signal from LACO. So here we have our received signal that would be demodulated to detect the symbols from the first layer. This would be like as ACO, the first symbol as ACO. And then these symbols are regenerating another OFDM signal to cancel the contribution of the first layer from the received signal. And this cancellation will allow us to detect the second layer here And then we would repeat this process until we detect all the symbols from all the layers. So here we will start our comparison of the three schemes that has been introduced: DC bias optical OFDM and asymmetrically clipped optical OFDM and layered ACO OFDM. So to have the same spectral efficiency for the three considered schemes, we are adjusting the QAM cancellation order, as you can see from the table. For spectral efficiency equal to 1, DCO would use only 4 QAM, ACO would use 16 QAM, and LACO would use 8 QAM for the first layer and 4 QAM for the second layer. And the same thing for the spectral efficiency of 2, we are adjusting the QAM order based on the spectral efficiency that we are using. So as you can see here, LACO has different QAM orders for each layer, so we can achieve the spectral efficiency needed. And we are using the same power for all layers, which means the same scaling factor for all layers. And for the simulation we will run, we'll almost use this electric transmit power of 50 milliwatts. And as you can see from the characteristics here, we are also ACO and LACO need also a bias, which is the minimum value here, as you can see from the graph. So first results is a BER, which is bit error rate plotted versus the distance between the transmitter and the receiver. And we plotted the DCO, ACO, and LACO for different data rates. Here we find 20 megabit per second, we have 50 megabit per second, and 100 megabit per second. And as you can see here, as the figure below, we have channel attenuation here. We are concerned about channel attenuation, and here we can consider about the saturation of ICPM. First, as we can see that the saturation of the red curve, which corresponding to DCO, is lower than ACO and LACO, the red and the blue curves, which is explained by the fact that DCO has a lower PAPR compared to LACO and ACO. This is can be explained also by the fact that DCO uses a lower modulation order compared to ACO and LACO. So as we can see here, the low BER interval for a target BER of 10-4, we have the LBI, the bigger one would be for DCO, but ACO offers the maximum attainable link range, which makes it a more power efficient scheme. This figure will plot with a spectral efficiency equal to 1, and as said before, for 15 milliwatt. Here we have the clipping effects on link performances. We are varying the power versus the BER, and here when increasing the power, we are concerned here by the clipping effect, because when increasing the power, we increase the clipping factor as well. So here we have that DCO outperform LACO and ACO in terms of clipping factor, the clipping effect, I want to say. So here, because we can be working under a wide range of power, it is not the case for ACO or for LACO. For here, when working under a low power, we can say that ACO is ACO outperforms the other schemes because it's the most high efficient scheme. I forget to notice that this curve are plotted for a distance of 20 and 70, is corresponding to a relatively moderate and high channel attenuation. And as we can see that one would expect the same clipping effect for all the schemes. And here we can show that for different data, for different distances, the ICPM saturation also has its effect here in the simulation, as you can see. So here we, to show better the clipping effect, we have plotted the performances of the three considered scheme using a color map. Here we have the transmit electrical power versus we have the distance here, and the color corresponding to the value of the BER, as you can see from the color map. So let's take, for instance, 200 milliwatt. We can see that here we are concerned about saturation from 0 to 10 meters. So here the ICPM saturation, so we can have a BER that is very high, which the red color corresponding to a BER, which is high. Here we have the flexibility of the LBI of DCO, and here we have channel attenuation. And as we can see that the clipping effect of ACO is huge compared to LACO and DCO. And we can say that DCO offer a lot of flexibility compared to ACO and LACO, but also LACO offers a best flexibility compared to ACO. So this results, or this color map has been presented for 20 megabit per second and for spectral efficiency equal to 1. Now let's see this the effect when increasing the spectral efficiency of 2. And here we are using only 20 milliwatts since the PAPR is increasing. So we have also the plot of PAR compared to the link distance for several data rates, 20, 50, and 100 for DCO, ACO, and LACO. And we can see that LACO over this time offered the best energy efficiency compared to other schemes with the maximum attainable link distance. And we can see here that ACO, even for low power, it starts to be clipping because it's using a high order modulation, So now we will talk about experimental setup that has been done so far in the lab, but we couldn't go through with it because of the pandemic. So we have here a block diagram of the generated the experiment. Here we have the bits or the of the signal generated by computer via MATLAB, and it's loaded to an AWG where we convert the digital signal to an analog signal, and then we feed it to the laser diode. Here the use of the laser diode is because we are using a water tank or an aquarium, and to extend the link range we are using reflections. And this is not to be done by using an LED. Our photodetector to detect the optical signal and transmit it to the oscilloscope, where we can convert the electrical signal to a digital one, and it will be treated later on by a computer to calculate the BER. So here's an image of the setup, which is, we can find the aquarium, we can find the mirror here to ensure reflection of the laser, and then the photodetector here to detect the signal, the received signal. Here the experiment performed in the dark, where we can see the laser beam being reflected through the aquatic channel, and it's been received here for the photodetector. So now we are concluding this work and give some perspectives about this work. So as a conclusion, first we used an ICPM to enhance the link range of optical wireless communication systems. We have introduced an optical OFDM technique to enhance data rate, since the bandwidth of the ICPM and the LED is limited. We have shown the advantage of using optical OFDM technique over OK in terms of the maximum attainable link distance and also the flexibility, which is the LBI that we have defined. We investigate the results using the limitation and the real characteristics of the emitter and the transmitter, and also using the required DC bias for each scheme. We have shown that ACO offers the best energy efficiency when working in the spectral efficiency equal to 1. We have shown also that LACO OFDM offers the best choice when the spectral efficiency is equal to 2, which makes a good compromise between PAPR, peak to average power ratio, and power efficiency. And we have shown later on that DCO remains the most flexible schemes, which offer the largest LBI and a more robust link. As a perspective of this work, we could carry out the experiment using the prepared testbed that we have shown and validate theoretical or numerical results via experimental setups. We could try to investigate the performance of LACO OFDM while adjusting the power of allocation between layers. We could also investigate other enhanced optical OFDM schemes that aims at benefiting from the loss in Hermitian symmetry to enhance the bandwidth as well for such schemes. And then we could study also MIMO architecture, which is multiple input, multiple output architectures to enhance the link, to enhance the data rate as well. So thank you for your attention.
Okay, thank you for your presentation. Actually, it was exactly 45 minutes, so your timing is perfect.
Thank you.
So now there is the time for discussion with reviewers. So at first, I would like to ask first reviewer, Professor Lauren Ross, to just present the review and ask questions, and you can immediately just comment or answer them. Okay, Ross, please.
Okay, thank you, Mr. President. Do you hear me? It's okay?
Yes.
Yes. Okay. So I would like first to thank Ali and Hassan for their invitation, and then I would like to thank Mr. T.ESSALIH for his presentation. So I find it very clear, very nice.
Thank you.
Yes, so perfectly in time. And I think you made good choices to not present all your technique and result and to focus on some. And the main result appear more clear to me in the presentation than in the manuscript where we have many things.
Yes, thank you.
Yes, so as I write in my written report, I have well appreciated the manuscript and the work. Yes, so in the crossroad of optoelectronic and digital communication. So even if the comparison stand on existing communication schemes, the additional value of the work is definitively that it takes into account practical impairment, what is not often done in the literature study. And also, I think you provide very clear, you have a very clear way to present a result with color map, very nice network of curves that will be useful, I think, for in perspective of the implementation of the wireless optical communication. So now I will ask some question. So perhaps first in slide 11, please. So here is aggregate channel. Could you please explain why in your manuscript you say that you take single path channel assumption? That means that each of channel is considered as the Dirac. Could you justify your choice regarding the order of the value of the other parameter, please?
Just to understand the question, you are talking about the impulse response of the channel, why it's neglected.
Yes, exactly.
There has been some studies. I referred to the work in the, in the presentation. There are some studies that shown that the delay spread of the optical channel when using a clear water environment are negligible. because the distance is limited.
Yes, you know what is the order of magnitude of the delay spread? Is there some nanosecond, less than 1 microsecond, to justify regarding to the?
I don't remember the value exactly, but it seems that is negligible. In fact, that's
Yes.
why we are considered the same thing.
Actually, yes, you have to say that it is negligible compared to the delay spread of components.
Exactly, yes.
And the cutoff frequency are 4 megahertz and 10 megahertz, so it means perhaps, yes, I don't know, 100 nanoseconds, so it should be less. Okay,
Exactly.
Thank you. Now, perhaps slide 16. Yes, about so you choose silicon photomultiplier, as you said, because this internal gain very high that permit to have a long range.
Yes.
But also, I am not specialist of components. So you explain that we have some distributed Poisson noise, dark noise, and short noise. Could you please explain if this kind of noise is specific to this component and not, for example, in classical pi-IN detector? And secondly, explain how do you simulate the noise in your simulation chain. Is it only Poisson noise? Is there also Gaussian noise? For me, it was not so clear in the manuscript at this point.
Okay, so when working in using ICP-M, we have a dominant short noise. So we neglect the Gaussian noise over Poisson noise. And the short noise is modulated by a Poisson distribution, which the mean and the variance would be the average photo count received for a given time symbol. And for the dark current, it is a parameter that concerns just the ICP-M. We can find dark current for other components, but I study mostly the dark current for ICP-M, which also, as you can see from the manuscript, that can affect the transmission of the signal when the value is very high.
Okay, and so in your simulation, you have only Poisson noise, and
yes.
you simulate the link between signal and noise thanks to this formula?
Exactly, yes. So this formula introduced the effect of dark noise and the effect of crosstalk and astropulsing as well.
Okay,
probabilities and
okay, thank you. Perhaps a question out of the scope of your work, but as noise is Poisson distributed, perhaps it could exist other scheme of modulations and conventional schemes that are actually derived from Gaussian noise with a correlator in the receive part, etc. Do you know if there is other scheme of repetition scheme to combat Poisson noise? So it is out of scope, but
sorry, I'm not familiar with such schemes. No, I don't know.
Okay. Yes, and just also about the dark count rate. Is it imposed by the component, or it is something? Yes, you don't tune it.
Yes, because we had contact with Hamamatsu, with the sales engineer. So they provide some essay that has been done in their lab, so where they showed that some figures about the dark current rate and the experiment in the dark, what's going on.
Okay.
And it's dependent also on the temperature of the component. That's why the component comes with a module where they trying to cool the temperature, so to have a lower DCR, so it not affect the performance of the system.
Okay, thank you. So slide 20, please. Yes, so in the left of the figure, we have a saturation effect with a bit error rate of 1. Could you explain? Because for me, it was expected that it was 50%. So if it's 1, it's good. We can.
Yes, in fact, the symbols are inverse in the case of OK. It can be explained by this figure. As you can see here, we have a linear region. So when we increase the power, we increase the photons. But in the nonlinear region, it's like when we increase the power, we decrease the numbers of photons. So like this curve is inverse here. So when we detect a 0, it's a 1 because the power is too high and the dead time is not respected. So it's like in inverse. But yes, in this area, we can say that we detect, we have a BR of 1 because we detected our symbol, it's just they are inverse.
Yes, but perhaps if we consider greater size of modulation, it could be more hard to detect.
Exactly.
No?
Yes, it will be hard because when using OFDM technique, optical FDM technique, we don't have a BR of 1, 0.5 in the saturation region.
Okay, so please slide 27. Yes, so in your work, my question is about the choice of OFDM, because it is not so common to use OFDM in a single path scenario, but you show that it is a good choice actually to investigate the bandwidth around and after the cutoff frequency of 4 megahertz and 10 megahertz, because without OFDM, with 1 bit per second per hertz of spectral efficiency, you will manage only 4 megabit per second, and with your technique, yes, you can transmit 10 times more, for example. So it's a good idea. So for this slide, I have some interrogation, because if we consider just 1 megabit,
yes.
I am quite surprised of the poor result of OOK modulation compared to DCO, because for 1 megabit, the spectrum is about perhaps 1 megahertz, and so we are in the flat frequency response of the channel. So I don't understand why OOK is so poor compared to DCO OFDM version, because we have no problem of ISI normally. And I think that if in presence of Gaussian noise, I should expect quite the same result. Perhaps I have not the good value in mind, but I don't know if you have.
In fact, this is dependent also, you should take also into account the time symbol. The time symbol in OK would be much less than the time symbol of DCO, because we are transmitting signal in 1024 subband. So
perhaps it is linked to the noise effect finally. No, because you say that for OFDM the noise was more independent. Perhaps it is linked to this. Or
yeah, yes, maybe there's that also, because I didn't consider any technique to separate the noise from the.
Yes.
From the
yes.
When using OK, yes.
So I don't make exact computation, but in my mind, if you use the same spectral efficiency without non-linear effect, etc., with Gaussian noise, I should expect quite the same result. And
because also the difference of the time symbol affects also the performance as well, because when changing the time symbol, the numbers of photons will change, so the parameters also of the ICPM would not be the same, so they will not count the same photons. That's my idea.
Oh, okay, so now a rapid question also, as we have to face ISI problem and also dynamic range and problem of PAPR, as you explained.
Yes.
In a previous work in your team, you know, I think the work of Tasnim Hamza.
Yes.
to face this problem, she considers single carrier modulation, but with additional cyclic prefix and frequency equalization.
Exactly, yes.
It could be also a good idea because PAPR is good, and I don't know if you have compared or if your new scheme, if you have a new view compared to this work that was done 4 years ago.
Yes, I didn't compare it, as you can see in results, didn't compare with this technique. This technique is preventing, when using OFDM, we have a simple equalization, which now would be the case for using
yes,
carrier modulation.
Yes, but if
and also the advantage over the noise dependency as well. That's
okay.
why OFDM it's more concerned, which is simple because we don't need to separate the signal from the noise.
Okay, so now my question is about PAPR issue. So perhaps slide 35, please. Yes, so I have some interrogation because I am a guy from radio frequency and not optical frequency. So I am not sure. In your manuscript, so here you show that we have the best, perhaps not in this slide, but on other slides, that we have the best flexibility, robustness of power with DCO OFDM. Okay, so I agree because we have a lower PAPR. So first, I think it will be interesting. It would have been interesting to present some PAPR distribution obtained in simulation because it is very important in your work. But so it's okay. And so my question is, in radio frequency, PAPR does not depend on the size of the modulation of M, because we consider Gaussian assumption thanks to central limit theorem, and then when the number of subcarrier is great, and it is your case, the PAPR does not depend on the size of the modulation. In your work, you say in your manuscript you said that PAPR increased with M. So perhaps it is a case in optical. I don't know. Are you sure of this result, that PAPR increased with M?
Yes, because for the LED that we consider, because we consider the same LED characteristics for all the considered schemes, and when adjusting because for my simulation, I adjusted carefully the scanning factor, which is the key to fix the transmit electrical power and everything. And I can see that the signal is more clipped for ACO than for DCO. So
yes,
I visualized that. I didn't calculate the PR distribution because for me it was obvious that it's a PAPR problem. But I ran some simulation to be sure that it's a problem of PAPR. When variation the scanning factor, and it was a problem of PAPR.
I fully agree that the waveform of clipped OFDM and other leads to increase the PAPR. I agree with that, but for me it is more perhaps the waveform AC OFDM that is less favorable than DCO OFDM than the size of the alphabet. But perhaps I'm wrong.
Okay.
So perhaps last important question to check in my manuscript. I say that formula of spectral efficiency of your manuscript should be revised.
Yes.
Formula 5.3, for example, in page 57. I don't know if you can go to, if you can share your your manuscript, or
Let's see. So,
if it's too long, I can explain without a formula, but
we just stop. What page exactly? You said 57.
For example, 57, yes. No, 57, 57.
Share the screen.
So here, as you see for ACO, you have a weight 1/4 in your formula, and it is normal. It is normal because it is divided by 2 with respect to DCO. But when you go to a formula obtained with ADO modulation or HADO, you didn't have this weight 1/4. I think it is an error.
It's
okay.
Yeah, yes. Okay. Yes.
So I think that yes, you have an error here. So be careful to correct, please.
Yes, sure.
And perhaps my last comment to let my colleague. So finally, in terms of flexibility, the most robust is the most conventional formula, the most conventional scheme, the DCO. So I think you were surprised of that or not in the beginning of your study? You think that?
Yes, I was waiting that LACO could offer the best performances, and I was surprised because there's a lot of schemes that they have been introduced in the literature, and you expect that they offer the best performances, which is not the case. And because remains powerful.
Yes, because of you have taken into account more impairment. So thank you very much.
Okay,
thank you very much, Mr. President. I let.
Thank you, and thank you for answers. So now I'll ask second reviewer, Dr. Eric Simon, to just present his comments and ask questions. Please, Eric.
Thank you, Mr. President. And first, I would like to thank a lot Ali and Hassan for inviting me to this jury. It was a pleasure to me to follow this presentation. So thanks a lot for this nice presentation.
Thank you.
I totally go along with Laurent Ross that it was not an easy task to summarize the numerous results of your manuscript. And so you made a very nice synthesis, and you really managed to emphasize on the main results. And we have the general trends of your results, and it's yes, it was nice to follow, and perhaps
thank you so much.
Easier than in the manuscript. There were lots of results, so here it was very complementary.
Okay, thank you.
I have some questions. If you could go on slide 25, please. Yes. So I'm not very familiar with clipping techniques, and in the manuscript it is not very detailed. So I must confess I had difficulties understanding this part on the whole. So could you please say how you fix the parameter alpha? What is the rule to tune this parameter?
In fact, the parameter alpha is the parameter key of this work, because alpha determines the optical transmit power. As you can see here, we have the scaled signal, the mean of the scale signal square. And since the QAM symbols are normalized, so we only have alpha square, which would be directly the clipping factor multiplied by alpha. And as you can see, the choice of alpha would depend on the DC bias that we are using. And both of these parameters, we can calculate also the transmit electrical power. So here the clipping factor is a factor that we use in dB. We variate it until we see the performances of the system for respected clipping factor. The scanning factor is also variated. That's especially with the APR, for instance, that ACO would need a lower scaling factor than DCO because it presented a lower and higher APR, for instance. And this parameter is variated, so we can see the performance of these schemes.
And so okay. And in that case, why is it an approximation here? When you in your equation?
Yes.
Because the expectation of x square.
Yes.
So it gives alpha square.
Yes.
I don't see where the approximation lies here
because when you do the calculation numerically, it doesn't give a 1, like 0.9 something. So it's an approximation of to 1. So numerically, because it's when we normalize the symbols, for instance, let's take for QAM, it will have values of 0.3 and 0.7, and it's not 0.33. Like there's a lot of numbers after that. So you can say 1, but it's an approximate 1, 0.9 something.
But theoretically,
theoretically it should be 1. Yeah.
Just,
since we are taking into account the real characteristics, so it's we are not in the theoretical part, so it's more into real part of all the component, all the characteristics of the system.
Okay. Okay. And then you mentioned it quickly in your presentation, but I would like to go back to this part. It's about the optimal way to calculate BDC.
Yes.
Yes, I have some question about it. It's not that clear to me how you consider the electric power in the formulation of the optimal approach. Could you please comment?
You want to show the optimal approach?
Yes. Yes, yes, if you can show it.
Just a second, please. Looking. So this is the technique, and it aims at minimizing the mean square error between the clipped signal and the scaled signal. And to do so, there was been some calculation that has been done by a paper that I've based on, where I took this technique. And based on the minimum value of the LED and the maximum value of the LED, and also the scanning factor, we can determine the optimal DC bias to use. And with these two parameters, the scanning factor and also the bias, we can determine the electric transmit power. by the characteristics of the LED, because we consider the OFDM signal as a voltage, and we calculate its image by current by bijection with the linear curve that I shown before, and we multiply the voltage by the current to have the electrical power.
So the electrical power, so it is calculated after the clipping?
The electrical power is calculated, but no, before
The clipping,
yeah.
in your formulation.
Yes, exactly. Yes.
Okay, and also because you also have to find the parameter alpha.
Not really. The alpha is variated. We fix the parameter alpha, and then we get the bias. Based on alpha, we have an optimal bias. So to variate the transmit electrical power, we variate alpha, and alpha gives us a bias, and then we could determine the transmit electrical power.
Okay, and do you think that you could also use a joint optimization for alpha and?
I thought about it at first, but it seems complicated to both because you don't know the signal that you will have, and you don't know you changed a lot of parameters. You changed the QAM modulation order. As you can see, there's a very complicated number of parameters for the simulations. And it seems that the more optimal way is to variate the scaling factor. And I show that by plotting a color map when we can show exactly what's happening when we increase the electrical transmit power, which depends on increasing alpha, when we change the distance as well, and it gives us the PER. I can say that from the color map that I plotted, we don't know, it's not required to optimize the alpha, the scaling factor, because it will give us a more high computational complexity, and I don't think that it would give a better results.
Okay. And the last point on this optimal approach. So you said then that there are lots of local minimum.
Yes.
And how can you be sure that you don't find the local minimum and not the global minimum?
In fact, this case, it was especially for the LED that we are used, because for another LED with another limits, we could have another curve, and we could have a curve that allows us to have one direct optimal DC bias. But in our case, I don't know, here we have a lot of values that approximate to 0, and this has been calculated numerically. So we cannot detect 0, 0. So it would be like a low value, a very low value. So it's like I took the points of this curve, and based on resolution, I could detect the lower value here and approximate it to 0.
Okay. And anyway, this is not the technique you used then, so you selected, so it's okay. I have now more general questions about the assumptions that you made. So you said that you considered a perfect synchronization, perfect channel estimation.
Yes.
And in your manuscript, you said that an error in synchronization or channel estimation will impact the OFDM schemes the same way. Could you please comment on that and give us some arguments?
Since we are sending we are sending signals through ACO, DCO, or LACO, so the signal will be clipped and then transmitted through the aquatic channel. So it would have the same attenuation and the same. So the effect of the channel will be the same. So when we change the alignment or change some parameters that would affect the schemes, we think that it would be the same for all the schemes. it will affect them in terms of performances the same way. Because when we are concerned, for instance, with link misalignment, it like the quantity of the signal received would be decreased the same way for the tree schemes, for instance. I understood your question well.
Yes, regarding the channel estimation errors, as it is a flat channel,
Yes.
I think yes, the impact is the same. But if we have a time synchronization error,
yes,
the answer is not straightforward, because with time synchronization error, the orthogonalization of the subcarrier is broken, and my intuition is that it will impact the different OFDM schemes not the same way, but
it should we should do a further investigation about this. I cannot say yes and I cannot say no. I understand what you are trying to say. Maybe we should do some further investigation about this this problem to quantify exactly what's going on for all the schemes.
Yeah, sure. And I have a last question about the perspective. So
yes.
you mentioned that the use of MIMO could be a nice perspective.
Yes.
So what have you got more precise ideas about that? So what's the point in using MIMO for your problem, and what kind of MIMO schemes? Could you please say a few words on that?
MIMO could enhance capacity of the signaling scheme. So by using multiple LEDs, we can use multiple LEDs for the transmission, as I shown in the manuscript, to enhance the link range by enhancing the power of the transmit signal. So this would offer to extend link range, but also to benefit from the use of multiple LEDs while transmitting, and also perform a MIMO architecture, which means we would have multiple ICPMs at the receiver, and this would increase the capacity mostly and the data rate mostly of the
because
channel. I suggested also for further investigation to use also to multiplex signal by wavelength. It's something that it's not. It is very complicated, I guess, but investigation could be done in this objective. So to see the effect of multiplexing through wavelength on the link performances.
Yes, because regarding MIMO scheme to enhance capacity,
yes.
in general, it's the MIMO techniques are very fruitful when the channel matrix, when all the elements of the channel matrix are IID, I mean I-dependent and identically distributed.
Yes.
But here, your channel model is that you have one path, which is deterministic.
In fact, it is considered as one patch. It's not the same, because if we take, for instance, scaling effect, it was our supposition. But if we take, for instance, what's going on, especially for turbid water, the scattering is present, and the light beam scattered through the patch, and we have a delay. So MIMO could work, for instance, when working under turbid water or hyper water, which is a classification of different kind of water. Yes, for clear water, MIMO would show less interest, I guess. I'm not sure. Further investigation should be done in this perspective, but MIMO could work when working under turbid water.
And in the literature, I think it exists, but
yes, they have already investigated the use of MIMO using ICPM as well on laser diode, and they proved great results in terms of data reach.
Mm.
And they apply the OFTM as well.
Mm. Okay, it's fine. Thanks a lot for this nice presentation.
Thank you so much.
Okay, thank you. So now there is time for questions from other panel members. So maybe at first I would ask Maria Roche if she has any questions, comments.
Okay, thank you. So first, I want to thank Ali and Hassan for the invitation for this jury. I want to precise that when they ask me, I accept without hesitation, as first of all, of course, the subject is interesting, despite the fact that it is not exactly in my expertise domain. Sorry. And the second reason is that I know Taha since 4 or 5 years, since he comes in the École Centrale Marseille for his 3rd year, and I was in charge of on the 3rd year of signal processing and image communication. So I follow Taha since this time, and I'm happy to see the evolution of his work and of his and to finalize this study step, because now you are working, and so I'm happy to participate to this step.
Thank you so much.
For the presentation, yes, as the reviewers has already said, I think the presentation was clear, well presented. The slides were nice, so I appreciate the presentation. For the manuscript, as I already said to you, Taha, I have some difficulties to read it for the first steps, because there were a lot of acronyms, and as I am not in the domain, I have difficulties to understand all the things you said. So I think it would be nice to improve that for your thesis, as the people who read your thesis are experts, but not only experts, and they need to fully understand what you say, and since the beginning of the thesis, and not at the end of the thesis. So yes. I think it's and sure. I want to precise that in your presentation today, it was better, and you have insist on acronyms, and you precise almost the time the acronym. So
exactly.
I think that
yeah, I will take this in consideration while correcting the manuscript after. And for each chapter, I will repeat the acronym, so it could be
yes,
understandable.
Nice. Yes. Yes. Okay. What? So for the question, I have some. First of all, if you have you tell us that you have made several hypotheses for your work, it is normal, but to simplify the calculus and so on, for example, for the turbulence, for the solar noise, for the misalignment, which were neglected, but can you have already spoke about it, but can you precise if this hypothesis of these things that are neglected, is it real?